All right, welcome back, everybody. It's a pleasure to have Mengdi Wang from Princeton giving a talk on policy gradient. Mengdi, take it away.
Hi, can you hear me?
Yeah.
Okay. Okay, so I have 40 minutes.
Yeah, sounds about right.
Cool. Okay, so we are going to talk about policy gradient. And so this is a series of work jointly with many very nice collaborators. So, okay, so we all know about policy gradient, right? So in reinforcement learning, sometimes we prefer policy-based method because maybe it could be easier to do optimization over a policy parameter space. Okay. And if we want to use policy-based method and if we want to use gradient optimization, so one fundamental result is the policy gradient theorem by Sutton, which basically says that if I want to evaluate the gradient of a value function with respect to its policy parameter, then this gradient can be written in the form of an expectation of cumulative sum over a sample trajectory generated under this exact policy pi theta. In the recent couple of years, I think the community has gained much deeper understanding into policy gradient. So there are a number of important questions to ask, and some of them are partially being answered, but there are still open questions that we hope to be able to answer further. So the first question is, how do we estimate policy gradient? So because if we want to use policy gradient and keep updating the policy, so what will happen is we are going to generate a large number of batches or episodes by using different policies. But however, if we want to estimate the policy gradient of a new policy, and then we're going to be entering the problem, which is off-policy learning. And when we have off-policy data, then the distribution shifts from older policies to the newer one. So this distribution shift becomes substantial. And the distribution shift also relates to how we actually make the updates. Do we do variance reduction or what learning rate we are choosing? And there's going to be large bias and even variance. So in practice, so it turns out that the most commonly used method is still importance sampling, which means that for older trajectories, we're going to assign a cumulative product of weights in order to do importance sampling and downweigh older trajectories. But however, whenever we do importance sampling, the most naive approach is going to generate exponentially large variance. So there are smarter ways to do that. But again, importance sampling requires dealing with distributions in a way to calculate importance weights, which is theoretically both theoretically unstable and practically it means that usually we have to be able to pick the window for importance sampling and also calculate weights carefully if we want to be able to get something more accurate. Okay, so further, we wish to be able to leverage function approximation for policy gradient estimation. So because there are tons of value-based methods for approximating value functions, for approximating Q functions, right? So one naturally asks, is it possible to learn the gradient of Q in a way that's similar to learning the Q function itself? Can we actually use the idea of value function approximation for estimating policy gradient? And thirdly, the theoretical question would be that, say that I only care about estimating a single policy gradient. And maybe this policy gradient is going to tell a physician which direction to improve his treatment plan. Okay, and we have a lot of off-policy data generated by different physicians. And then statistically speaking, what is the optimal estimator of a single policy gradient? And how to characterize the estimation error. Okay, so that's the problem of estimation. And say that we have policy gradient or a very good estimator for policy gradient. So the next question is, okay, we want to use policy gradient for optimization. And the first issue is going to be that policy optimization has a very complicated and highly nonlinear, non-convex landscape. So recently there have been very insightful works trying to analyze global convergence of policy gradient when the policy is either tabular or softmax. So we do understand that for particular tabular or softmax policies, although without convexity, one can actually have global convergence to the optimal solution. But more generally, then there's really not much one can say about global convergence. Okay, so beyond the landscape, so say that, okay, we want to be able to estimate policy gradient while updating the policies, and we want to find an optimal policy. So can we combine a better PG estimate with a smarter algorithm? And what is the best sample efficiency we can get for policy optimization? And even more generally, so in this talk, we hope to be able to extend the scope of policy gradient methods to solve problems actually beyond standard reinforcement learning problems. Okay, so firstly, policy gradient actually has its own Bellman equation. So the policy gradient Bellman equation can be proved fairly straightforwardly by just differentiating both sides of the Q function Bellman equation with respect to the policy parameter. Okay, so that basically means that if we know the Q function at stage h+1 and its gradient at stage h+1, and then they should be able to give us the gradient of QH with respect to theta. So having this Bellman equation is important because we do know that Q-learning and many value-based algorithms are based on Bellman equation. So if policy gradient has its own Bellman equation, that means that we may be able to learn policy gradient functions in a way similar to learning Q functions. Okay. So we propose a double fitted iteration for estimating policy gradient, which is basically in the same spirit with fitted Q iteration and fitted Q evaluation. So what happens is, as long as we are given a function class and we may have a batch data, they can be generated either on policy or off policy. Okay, then we can always do iterative regression to try to fit the Q function and the Q gradient function together recursively by minimizing least square error over the function class. Okay, so this is actually a fairly straightforward approach if you know fitted Q or fitted Q evaluation well enough. You will know that this is going to be a fairly easy to implement approach because we only need to do regression and we can easily use any neural architecture. And this algorithm actually is very simple conceptually. So doing fitted Q iteration or fitted Q evaluation or fitted PG iteration, so they are both equivalent to a model-based plug-in estimator. So plug-in estimator means that whenever we have a batch data, if we try to project the transitions in the batch data to our function class, then essentially we're getting an approximate transition operator, which is an estimate of the transition model of the MDP. So Q hat and gradient Q hat are actually all model-based estimators. So they're equivalent to that we estimate the model first, and then plug in the estimated model transition operator to compute the corresponding policy gradient and corresponding Q. And another interesting insight here is that in the simple case of linear MDP, the policy gradient estimated by this algorithm is actually exactly the same with we first estimate the Q function, we get a Q hat, and then we try to differentiate the estimated Q function with respect to theta. So this may be actually something people want to do practice, because in practice, we often approximate Q functions very well. But however, even if we can approximate Q functions, numerically it's challenging or even intractable to differentiate this approximate Q function with respect to another policy parameter. But this algorithm says that if we do this fitted iteration, the outcome of estimator is equivalent to estimating Q and differentiate it. Okay, so we try to analyze the statistical error bounds for this policy gradient estimator. Notice that our data can be very easily off policy, and there could be significant distribution shift. So we're able to show that the estimation error has a finite high probability error bound, which is largely dominated by a covariance term, which we call lambda theta. So this covariance matrix is too big, so I didn't include it in the slides. And one can, we also provide a companion Cramer-Rao lower bound, which actually says that this particular variance aware upper bound is statistically optimal, meaning that the fitted iteration gives the best possible policy estimator, even in the off policy training case. So it should be the estimator with the smallest error bound and variance. Okay. So further, there's a very intricate insight here. If we try to really delve deeper into the estimation error bound analysis. So because right now we're using function approximation to approximate Q function and Q gradient function, right? And also we're dealing with off policy data. We do know that off policy data creates a distribution shift, and distribution shift sometimes can jeopardize the entire estimation problem and generate and leads to significant substantial estimation error. But on the other hand, we are also using function approximation. We are approximating Q function and its gradient function. So function approximation is supposed to be able to improve generalizability and improve prediction accuracy. Okay, so we try to refine the error bound and to get a reward-free version of the error bound. Okay, so one can show that the policy gradient estimation error is actually bounded by a very interesting term here. So it is the square root of a particular divergence function between the batch data distribution and the target policy's occupancy measure. Okay, so that particular divergence, which we call it the F-restricted chi-square divergence, it turns out to be the single important quantity here to characterize the hardness and statistical complexity of off-policy estimation. Okay, so this is a divergence function defined in a variational dual form. Okay, and it depends on the function approximator class we are using. So basically, we're trying to take sup over functions in the function class, and we're taking supremum of this term that measures some sort of chi-square divergence between two distributions. But however, because this divergence is defined by taking sup over a function class rather than taking sup over the entire L infinity ball. Okay, so this divergence can be actually very small if the function class can annihilate distribution shift. So in other words, the fundamental statistical error of off-policy estimation is determined by how distribution shift and our function class are coupled together. And the function class restricted chi-square divergence can be substantially much smaller than the non-restricted plain vanilla chi-square divergence between the two opposite measures. And even without function approximation, the chi-square divergence is going to be substantially smaller than the L infinity norm between the density ratio. And in most existing works on analyzing distribution shift and sample efficiency, statistical error is usually characterized by L infinity norm of the density ratio, which is only finite when the two probability density functions are extremely close to each other. But this theory says that actually, even if the two opposite measures are very different, the distribution shift can be arbitrarily large, but as long as the relative distribution shift in the function class is small, one can get good estimate. And we can further show that this error bound is min-max optimal. Okay, so that's the story for optimal estimation of policy gradient by using function class. Okay, and then next, we aim to study a problem class which is broader than classical Markov decision process. Okay, so in classical Markov decision process, we all know that MDP, by definition, we're dealing with additive rewards. Our objective function is expectation of sum of rewards. So we take this by granted. And because we worry about sum of rewards, then we can define value function of state, which is expectation of sum of rewards. And because we have such definitional value function, then one can show Bellman equation, which says that value of current state can be decomposed into sum of immediate return and sum of future value. And further, because of this additivity, one can show the policy gradient, the classical policy gradient theorem. So we take the value function, the Bellman equation, the policy gradient theorem all for granted. But however, additivity of rewards is actually a pretty strong assumption. And in many applications that we care about, we might actually look for we might actually search for policies to maximize non-additive rewards. Okay, so let me give you several examples. Okay. Again, we can work with Markov decision process, but let's consider more general objective functions. So one example is if we want to do exploration in a brand new environment. So we care about maybe visiting every possible state. But however, it's very hard to model this objective as a cumulative sum of rewards. For example, if we try to augment the state space by memorizing all the states that have been visited, then we can make the reward additive. However, this augmentation is going to make the state space exponentially larger than the original state space. Okay, and secondly, we might want to be dealing with safety concerned applications and also risk averse applications. We do know that expectations and sums are risk neutral, but what if we care about a more general coherent risk function? And thirdly, sometimes we want to do imitation learning. So we might have some known data set, either some existing players' experience, or we might have some summary statistics or marginal state distribution observations about other players. And when we train our own policy, we want to regularize our policy using the data or the known distribution we have to do some sort of imitation in order to train faster. So all of these different objectives, they are pretty natural and common, but they are not sum of rewards. Okay. So these new objectives, they actually fit into a slightly broader mathematical framework. So we consider here reinforcement learning for general utility functions. So say that, okay, we're still trying to maximize to find a best policy pi theta. And we care about its utility function, we call it R. some R utility function of the policy. And we say that this utility function is going to be a functional of the state action occupancy measure generated by this policy. So we want to directly optimize a policy to figure out a preferred long-term state action distribution rather than a single sum of rewards. Okay. And we're going to consider concave function f, which operates over the policy's occupancy measure. Okay. Note here that because we are no longer dealing with additive rewards, there are many things that we took for granted in classical MDP theory no longer hold. So here we have to prove again that for this more general convex Markov decision problem, it's actually okay to only explore over stationary policies. Cyclic and non-stationary policies not going to make our objective function bigger. Okay, so the prior examples actually all fall into this category for general utility functions. So first, in standard reinforcement learning, we deal with cumulative reward. So the value function of a cumulative reward is exactly the inner product between the occupancy measure lambda and the reward function. So basically, the functional f is linear for standard MDP. And if we want to do exploration, we can simply pick the f function to be the entropy of the state visitation distribution, which is again concave in lambda. So in the case when we have state feature map, and we may care about exploration in order to generate well-conditioned data and cover the feature space. In this case, a natural objective would be to maximize the smallest eigenvalue of the state features covariance. And again, this objective is a concave function of the full state action occupancy measure. And the last example of imitation. For example, if we know the marginal state distribution generated by some adversarial player, but we don't get to observe his moves. Okay, so we can still try to regularize our policy to make our policy's state distribution to be close to the expert's state distribution by using a negative divergence, Kullback-Leibler, or any other reasonable divergence function. And again, this is a concave utility function. Okay, so now what's really interesting here is that if we return to the very basic of a mark of MDP and reinforcement learning theory, we quickly realize that almost the entire theory of Markov decision process relies on the fact that we are working with cumulative rewards. So if we consider a more general utility function to maximize, we no longer have additive rewards. So the consequences are that first, we no longer have value function because value is sum of rewards. Now we don't have additivity. And also we no longer have Q function. They just don't exist. And then because we don't have value, we don't have Q, then dynamic programming and the Bellman equation, they all no longer hold. Okay. So, so basically we have to give up on value-based algorithms. So finally, let's return to policy optimization. So since we don't have value-based algorithms, can we still directly optimize over the policy space? Or can we still directly search for the optimal parameter in the policy parameters space? And can we still have algorithms that can be easily implemented? Okay. I think I'm going to skip this slide since we're running out of time. Okay. So in order to still be able to do policy gradient or policy optimization, so the first step is we need to be able to evaluate the policy gradient for this more general problem. And we can imagine that policy gradient theorem doesn't hold anymore because policy gradient theorem is proved with reward additivity. Okay, so in the policy gradient theorem, first, we no longer have this Q function. And secondly, this entire expectation of sum structure no longer holds. So we have to be able to evaluate or compute policy gradient for this more general problem in a different way. Okay, so now let's work with our general utility function R of pi theta. And we want to find its gradient with respect to policy parameter theta. So the utility is a composition between the function f and the mapping from policy to occupancy measure. So one might say that, okay, let's just use the chain rule. But because inside the composition, we have an entire state action distribution. So if we want to use the chain rule, then we have to be able to estimate the entire state action occupancy measure. And we also need to be able to estimate the gradient of the distribution with respect to theta. And we all know density estimation is a problem that is hardly tractable. And estimating its gradient is even harder. We don't want to solve a simpler problem by first solving an even harder one, because the policy gradient itself could have much smaller dimensions than the state action occupancy measure, right? We're doing parameterization. Okay, so it turns out that if we return to the fundamental optimization structure of Markov decision process, one can show that the policy gradient for this much more general utility function is equivalent to the solution of a min-max optimization problem. So the trick here is actually very simple. Because we're dealing with a nonlinear concave utility f, we can simply go to its ventral dual, and we're going to introduce a dual variable, which can be viewed as the shadow reward function. We no longer have reward, but in the dual form, we have a shadow reward, which is the dual variable. So, and if we know we have the perfect dual variable, which is actually going to be the cutting plane, which is going to come from the cutting plane of the utility function with respect to the state action occupancy measure. So if we have that, then we are going to know the policy gradient immediately. And if we don't have the shadow reward, then one can try to solve the min-max optimization problem. Okay, so this is not an algorithm yet, but at least we have a formula to write down what the policy gradient is when we no longer have cumulative sum as objective. Okay. So now can we estimate the variational policy gradient by solving the min-max optimization problem? Because the min-max optimization problem looks like a high dimensional problem, right? That doesn't make sense to solve this high dimensional problem. So it turns out that we can solve it by just using Monte Carlo sampling. So for example, a very straightforward plug-in approach would be to just generate on-policy sample trajectories. And then we can approximate unknown function and quantity in the min-max optimization problem by taking sample average over the trajectories. And then we have a stochastic min-max optimization problem, which is going to give me an estimator of the policy gradient for general utility function. Okay, and in order to solve this problem, one can use any kind of, for example, stochastic primordial gradient or accelerate stochastic primordial gradient. So this is actually a problem that has many tractable solutions to solve. Okay. And I think a more important question is, say that we do this Monte Carlo sampling and we try to solve for a stochastic saddle point. Is the solution really going to be useful? Because the min-max optimization problem has high dimensional functions involved. And we definitely don't want to introduce high dimensional noise because fundamentally we're trying to only get a single gradient. Okay. So it turns out that in theory, one can provide estimation error bound for estimating the policy gradient via stochastic saddle point problem. And estimation error is only determined by smoothness of the objective function rather than underlying dimension of state space, action space, or the probability density functions. And the proof is based on analyzing the stochastic stability of saddle points when objective functions are perturbed with additive errors. Okay, so the short story is, yes, indeed, when we no longer have value function or Bellman equation, we actually can still be able to write down the formula for policy gradient. And we can actually still be able to estimate the policy gradient by stochastic min-max optimization. And one can prove statistical error bounds that are polynomial and tractable. Okay, so now we have figured out how to estimate a single policy gradient. And now we want to return to the entire optimization problem. Recall that in policy optimization, so my policy parameterization can be a neural net. And the mapping from policy to state occupancy measure and then to the general utility. So there's no known structure. It can be an arbitrarily non-convex mapping. So the problem itself is definitely highly non-convex. Okay, and this non-convexity holds for both standard MDP and the MDP with general utility function. Okay. However, if we try to dig into the landscape of Markov decision process, we do know that the problem we have in mind maximize some utility function over policy space. This one is non-convex. But however, this problem is equivalent to another optimization problem in the space of occupancy measure lambdas. So in the space of occupancy measure lambdas, the optimization problem is to maximize a concave utility of lambda. And the constraint is that lambda has to be some occupancy measure corresponding to a stationary policy. So this constraint is actually the intersection between a big linear system and the non-negative simplex. So the constraint in the space of lambda is actually a polyhedral, which means that the problem, if we view it as a problem in an optimization problem in distribution, it's a very nice convex optimization problem. Okay, and if we exploit this structure and under proper assumptions, for example, if we have a one-to-one mapping between our policy parameter space and the space of lambda, or if my parameterization of policy is sufficiently expressive so that the problem can be still mapped to the nice convex optimization problem where lambda belongs to a polyhedral. Okay, as long as my policy parameterization doesn't change this particular hidden convexity structure, then we can actually show that as long as we can find a stationary solution in the policy parameter theta space, that solution is going to be globally optimal for the entire policy optimization problem. Okay. And based on this hidden convexity, one can actually further analyze iteration convergence and iteration convexity of policy gradient ascent. Okay, so let's say that we don't have any estimation error. We have some oracle that gives me exact policy gradient at each theta. So we just run gradient ascent. And then one can show that in general, this algorithm actually converges at a rate of 1/t, with t being the number of iterations. And in addition, if in my objective function, we have, for example, some Kullback-Leibler divergence, which is strongly convex, one can actually make the algorithm converge faster or even exponentially. Okay. So the analysis is actually, I think, conceptually very easy. So analysis is, although our algorithm works in the theta space, But when we try to analyze the convergence and the reduction of optimality gaps, we are going to translate the convergence analysis to the lambda space. So although in the theta space, the convergence and updates may look wiggly, but however, the gradient flow is very nice and simple in the lambda space. So one can actually analyze convergence of policy gradient methods as if we're analyzing with convexity. Okay, and again, if we go back to the standard problem when we have cumulative reward, the problem in the lambda space is a linear program, and all the assumptions naturally hold with tabular MDP, and also with a softmax under a little bit of modification. And in this case, the iteration complexity of policy gradient is actually going to be of order 1 over epsilon. And that's actually much better than the 1 over epsilon square iteration complexity that used to be known. Okay. And finally, so we want to put together estimation and convergence. So there is a particular algorithm which is too long to show in the slide, but there is an algorithm that combines estimation and convergence, which is really just a gradient ascent algorithm, but uses a more accurate estimator for policy gradient. Okay, and one can show that solving the Markov decision process with both cumulative rewards and general utility, the sample complexity is 1 over epsilon square. So this sample complexity is not surprising because we do know that in tabular MDP, in linear MDP, when we use other methods, when we use other value-based methods, the sample complexity is 1 over epsilon square. That's pretty much that's very much expected. But however, in policy gradient convergence analysis, the best sample complexity one have ever got before was 1 over epsilon to the power of 3. So which means that there used to be this big gap between sharp theory for MDP and theory for policy gradient sample complexity. And we're finally closing this gap. And also what's interesting is if we try to compare those convergence results and sample efficiency results with convex optimization, so one can conclude that actually both iteration complexity and sample complexity for solving this general utility RL problem is actually comparable to stochastic convex optimization, which means that the problem is actually, from an optimization perspective, is actually not as hard as we might have expected. Okay, so this is the last slide and the summary of the talk. So first, we consider how to get min-max optimal estimation of a single policy gradient. And we show that policy gradient has its own Bellman equation, which means that we can actually do function approximation and function fitting to estimate policy gradient in a way that is very similar to estimating value functions and Q functions. And along this line, we can provide statistically optimal error bound for policy gradient estimate. And the error bound is determined by a particular divergence quantity that describes how distribution shift is coupled together with the function class. So the better function class we use, definitely we have smaller error, even if we could have very big distribution shift in the original state action space. And then if we consider solving policy optimization problems for objectives that are beyond cumulative rewards, although we no longer have value and Bellman equation, one can still be able to estimate policy gradient by solving a stochastic saddle point problem with statistical guarantees. And finally, the entire landscape of policy optimization can correspond to a hidden convex optimization problem in the space of optimization measures. And if we do the analysis in the correct space, one can actually show that the iteration complexity is as good as 1 over epsilon, comparable to convex optimization. And the sample complexity is 1 over epsilon square, which finally matches the known lower bound for MDP theory. Okay, so that's the end of my talk. Thank you.
Thank you, Mengdi. Any questions for Mengdi?
Hi, Mengdi. Yeah, very insightful talk, actually. So I was curious about this variation policy gradient where you showed that stochastic min-max optimization. Can you go back to the slide? I was wondering, like in the special case where you have this additive reward setting, what is the interpretation of that min-max reformulation?
Oh, in the additive reward, we just don't have the do variable. Let me find it. Yeah,
Here,
a good question. Yeah, in the because we don't have additive reward, we're actually having another inner minimization over a do variable, which is like a surrogate to the reward. But when we don't have it, then it's really just a simpler optimization problem.
I see. So there is not like any reduction to what's known in because there you have like there is a way to compute the policy gradient there.
It does reduce to the known policy gradient theorem, but it requires a little bit of convex analysis because in the typical case, the conjugate of linear f, so there will be we need to do some analysis to show that.
I see. Okay, interesting. And then for the stochastic stability there, you mentioned that the 1/n sample complexity or the 1/n bound only depends on the smoothness.
Right.
Does the smoothness parameter depends on the state action size or is
no, the smoothness is determined by the objective function and it basically determined by the optimization problem. Yeah, for example, like if we I think for example, it can depend on the L infinity norm of the gradient of the objective function. But if the objective function is linear, the L infinity norm of its gradient is really the L infinity norm of the reward, which is usually considered as 1 in classical MDP.
I see. Interesting. So there's no dependence on the state action at all. Wow. Okay.
No.
Yeah. Thanks a lot.
Thank you.
I have a question about the when you took the Fenchel dual in the previous slide. I think, yeah, the same slide that Nia asked you about. Actually, could you explain like what is V exactly, and like yeah, so what is this V function?
Oh, this V function is going to be the value function of the value function using policy seed pi theta when the reward is given by Z.
Oh, I see. So that is a sort of like hallucinated value function.
Yeah, it can be sort of like, yeah.
Okay.
Yeah. Yes, it's pretty much like we're like sort of like doing cutting plane optimization. So whenever we have a shadow reward, the cutting plane becomes a linear problem, which gives me actually a value function corresponding to the gradient or the corresponding shadow reward.
Thank you.
So you mentioned that there's no, value function when you have this general concave nonlinear big F, but you can define like local value functions where at any given policy you look at the first order approximation.
Yes, you're right. Yeah, that's actually the first order approximation actually corresponds to the do variable, right?
Okay, I was going to ask if there's like any interpretation, but I guess you answered that.
Yeah, that's exactly the interpretation. Thank you for asking.
All right, so thank you again, Mengdi.
Thank you guys. Thank you very much.
And we'll be back for the last talk in